All right, so we got this displacement vector in three different ways in the last video and showed that it was all the same vector. We came up with the same answer. And there's one more piece of information that goes with the vector. We got the magnitude, but as we now know, vectors have magnitude and direction. And in one dimension, if we're just traveling left or right or up or down, we just decide which direction is positive and which direction is negative, and we know the direction based on the sign of the magnitude. But in two dimensions, that's not the case. In two dimensions, the direction is usually given by the angle with respect to the horizontal. And sometimes it can be a different angle, but that's the most common one, the angle with respect to the horizontal. In three dimensions, it can be an angle with respect to whichever axis you choose. But we're just going to focus on the two-dimensional case right here. And so the angle with respect to the horizontal of our displacement vector is going to be this angle right here, and we'll call that theta. So how do we find theta? We know the magnitude, and we got that just from these y and x components, and we can also use those components to find the angle. So this y component here, this length 10, this is the side of the right triangle that is opposite of our angle. We're just going to use the fact that these components in the hypotenuse, or these components in the vector itself, form a right triangle. So that's the opposite side. And then this 19 length horizontal component is the adjacent side. So we have the opposite and the adjacent sides. And if you recall from geometry, if we have the opposite and the adjacent sides, we can use tangent. So tangent of this angle is going to be 10 over 19. And so if we want to find the angle itself is going to be inverse tangent of 10 over 19. And if we just type that into a calculator, inverse tangent of 10 over 19, that gives us an angle of about 27.76 degrees. So this angle right here is about 27.76 degrees. All right, so we have our angle and we found our magnitude. In general, the way we do that, if we have any vector v, the magnitude of a vector v is going to be the square root of its x component squared plus its y component squared. And if you have a three-dimensional vector, then you would just add the third component, the z component squared. And the angle, in this two-dimensional case, the angle can always be given by inverse tangent of the y component, so we'll say vy over vx. So that's for any vector v. In our case, our vector was r, and so we use the respective components. Now, that's our r. Now, what about average velocity vector? So this is on its own over here. We said we can have an average velocity vector, and we said that that average velocity vector was the displacement vector divided by the change in time. Well, our change in time in this case was 1, and we found our displacement vector up here. Our displacement vector was 19 I hat plus 10 j hat. So this is the vector 19 I hat plus 10 j hat. And dividing by the time change is the same as multiplying by 1 over the time change. So this is being multiplied by 1 over, in this case our time change was just 1. So our average velocity vector is just going to be this vector right here. Multiplying by 1 over 1 doesn't change anything. So that's our average velocity vector. But what about our instantaneous velocity vector? We can get our instantaneous velocity vector by deriving. So we have the position vector that was up here. This was our t cubed plus 2t squared. So actually, let's get a copy of that and bring it down here. So this was our original position vector. And if we want the instantaneous velocity, we can say the instantaneous velocity vector is given by the derivative of the position vector with respect to time. And in this case, when we derive vectors, in any case, when we take the derivative of a vector, we take the individual derivatives of its components. So each individual component. So that first component there, t cubed, its derivative is going to be 3t squared. So our first component of our velocity vector is 3t squared I hat. And our second component here, the derivative of 2t squared by the power rule is just 4t. So we get 3t squared I hat plus 4t j hat. And this instantaneous velocity vector right here, I've got mapped out down here. So this is another screen grab from Desmos, and this is just our instantaneous velocity. All right, so we want to find, let's say we want to find the displacement or the change in velocity. So displacement in velocity doesn't make a lot of sense. We want our change in velocity from, we'll use the same time, from t equals 2 to t equals 3. That's what we're looking for. So we're going to calculate that. We're not going to go through all three ways of calculating that. We'll just do it one way. So let's figure out what our velocity was at these times. So our velocity at 2 seconds or minutes or whatever our units happens to be in the scenario, we get 2 squared, which gives us 4, and then times 3. 4 times 3 is 12. So this is 12 I hat. Now 4 times 2 gives us 8, so this is 8 j hat. All right, and what about at 3? So our velocity at 3 is going to be 3 squared times 3, and that's going to give us 27. So 27 I hat plus, and then 4 times 3 is going to give us 12, so that's going to be plus 12 j hat. And if we want our change in velocity, we're going to subtract the two. So we want to take v at 3 minus v at 2. And when we subtract vectors, again, we just subtract the components. So 27 minus 12 there is going to give us what? It's going to give us 15 I hat. So that's 15 I hat. And then what is our j hat component? It's going to be 12 minus 8. That's going to give us 4 j hat. 4 j hat. So our change in velocity vector is 15 I hat plus 4 j hat. So let's go ahead and map that out. So we want 15 in the horizontal direction, so that'll land us right there. And we want 4 in the vertical direction. That's going to land us right there. So notice that this point here is not on the graph, and that's because this is just going to represent a change in velocity. If we wanted to mark these 2 points, we could, and then we could get the vector the same way. So this 12 I hat plus 8 j hat, the point 12, 8 is right here, and then this 27 I hat plus 12 j hat, that point is way over here. And the vector from this point to this point, the change in velocity, is going to be the exact same vector that we just got by subtraction here. So this vector right here is going to be our change in velocity. That's going to be our change in velocity. And we could go through and find the magnitude and everything, and the process would look exactly the same. We know that this component here is 15. We know that this component here is 4. And so I encourage you to try to calculate the magnitude of this vector yourself using these components and the Pythagorean theorem. It's just finding the length of the hypotenuse of this right triangle. And the last thing we can do, we can get our acceleration. We can get our acceleration vector. So if we just, let's take a copy of this, move it down here. So if we want our instantaneous acceleration, well, acceleration vector we saw is just the derivative of the velocity vector. So if we're taking the derivative, again, we just take each component. So 3t squared, the derivative of that is going to be 6t, so that's our I hat, that's our horizontal component. And then the derivative of 4t here is going to give us 4, so plus 4 j hat. So our instantaneous acceleration vector is 6t I hat plus 4 j hat.